So we're here today to take the wraps off of a stealth skunkworks project that a few of us at VMware have been working on for about 3 years now. This is not a product announcement. This is really a tech preview, and the reason why we do these sessions is to expose to you the kind of things that we're working on internally, to get feedback from you so that we can kind of learn about what things to prioritize over others as we try to think about taking these ideas to productization. This is just some cool stuff that we've been playing with in the labs, and we hope eventually something will come of it, but none of this is a promise of that. And cue the disclaimer slide. You've seen this enough, I won't spend any time on it. So here's a quick outline. I want to walk through this so as we talk, you have a little bit of idea of what's to come. And just to let you know, because this is the last session of the conference, I have saved the best stuff for the last couple of slides. You're going to have to hang in there. And I promise you it'll be worth it. I've given this session before, and the folks who hung around to the end really walked away with some interesting ideas on how to go back and optimize their environments. Okay, so we'll start with the problem description and motivation. And my objective in that first section is to channel storage or VC administrators. And the pain that you guys feel, I'm going to walk through a couple of examples of the types of things we're going to try to address. Then I'll hand over the podium to Minwen, who's going to be talking about storage DRS, with the abstractions that we're trying to introduce, some of the feature sets to give you an idea of what we're working with. I should also give you some UI mock-ups and talk a little bit about space and I/O load balancing. I'll focus mostly on the I/O load balancing part, and then we'll conclude. As far as questions are concerned, clarifications are welcome during the talk. For some of them, I'll just defer them to the end. But please don't mind if I do that. But let's hear them anyway. Okay, so in the data center today, with the feature set that VMware has provided to our customers, the data center automation state-of-the-art involves a couple of different things as far as resource management are concerned. Now, there's a lot of other feature sets. Today, I'm really talking about resource management. DRS, of course, actually, it's a good time to ask, how many people use DRS in production today? Okay, there's still a few of you who are not doing that. What's going on, people? Okay, well, those of you who didn't raise your hands, talk to your neighbors, see if they can help you out. More serious question. How many people use it for production workloads in automated mode? Wow. Okay. So this really speaks to the confidence that you have with regards to our algorithms, doing the right thing and giving you the peace of mind. So, of course, DRS is using vMotion to balance CPU and memory resources across the cluster. This was a serious problem that VMware DRS addressed to the point where our customers don't even think about this problem anymore. Now, that's not all. We have actually, since then, in vSphere 4.1, introduced a new feature called Storage I/O Control that I alluded to earlier. And this is a really important feature. A year ago, I was probably in this very room talking about the tech preview of that feature, okay, and getting feedback from our customers. And what we heard was, look, this is really important. Get it to us as fast as possible. And that's what we did. Even if we had to take a couple of compromises here and there, we've tried to deliver it to you as fast as possible. We actually had 3 talks for Storage I/O Control. How many people attended any one of those talks? That'll give me an idea of kind of things that I should not focus on. Okay, so about less than half. My understanding, my expectation is that folks in this room deal with storage every day. If you deal with storage, you need to go and look up the video for that talk. It will make your life easy, and it's available right now, compared to what I'm talking about, which is not yet available. Of course, you can learn a lot of lessons from this talk, but you really can make your life easy starting today. So, Storage I/O Control, what does it do? Well, fundamentally, it fixes the noisy neighbor problem. Now, we all know that the noisy neighbor problem, as far as memory and CPU is concerned, is addressed by DRS. It provides isolation for CPU and memory resource consumption, which means your VMs are protected, or your customers, your clients' VMs are protected against other VMs that may start to monopolize the resources as far as server and CPU and memory are concerned. Well, we're trying to do the same thing for storage. This is a really hard problem. It took us about 4 years to crack this problem from the time we started working on it to the time we shipped it. Really, really interesting and tricky problem. but we think we've done a great job at it. It also provides proportional sharing of shared I/O resources, which means that if you have more important VMs, then you can assign them higher shares, and they'll get higher priority as far as storage I/O is concerned. So, very cool stuff. We have DRS, we have storage I/O control, but there is still an elephant in the room. And that's what I'm going to talk about next. So, what often happens is, so let's skip this animation. What often happens is that when a vCenter or IT admin gets a new application to deploy, there's a couple of different things you have to do. You have to find a server to put the CPU and memory execution on, of course, but we have DRS for that. Now, how about the virtual disk? Where are you going to put the virtual disk? You have a certain number of data stores that are connected to that DRS cluster, but which data store are you going to pick? Now, in this example, I've just really made it simple, and I have 3 data stores. And in this case, they happen to be space balanced. Okay, those virtual disks, let's assume, are about the same size. So the administrator says, look, where am I going to put this new virtual disk? Okay, eeny, meeny, miny, moe, we'll put in the middle one. Okay, seems fair enough. Well, we did that, and turns out that data store became overloaded. Now, when the IT administrator was picking that data store, he or she was not aware of the detailed situation that data store was under. And so it was just a mistake. In fact, to be honest, the administrator still doesn't know that there's an overload because he's or she's not monitoring constantly. This is completely oblivious. He's oblivious to this. But not for long, because he probably did this at night, and his phone's going to start ringing off the hook as soon as users come in the next morning. Okay. So it's 8:30. He shows up. Probably didn't shave. Okay. He shows up. And he's got to figure out what the problem is. He's got, 50 users trying, just upset. So first he says, okay, is it a CPU and memory problem? Looks at DRS, does the stats collection, no problem. DRS is running, no faults, no issues. Okay, an hour's gone by. Now he thinks it's a networking problem. Okay. Another hour goes by, there's not a networking problem. Now he thinks it's storage. There's nothing else left to do. And by the way, the reason he kept storage to the end was because he was hoping to get lucky, because storage problems are really hard to diagnose. Okay. So now he's convinced that it's storage, and so he's going to go in, and he's going to say, well, what is it? Is it a data store? Is it some application? Where is the problem? So he's got to narrow down to the right resource, but he doesn't know which data store it is. So he does some analysis, another hour goes by, he figures out it's a middle data store. And now he knows that it's a middle data store. But what's he going to do? He's going to do storage vMotion, like all of you folks. But where is he going to store vMotion to? He could go to the top one or the bottom one, but he's sitting there sweating right now because he doesn't know if he puts it on one of those, whether that one's going to get overloaded, right? So this is the problem. Now, if he gets lucky, he does the storage vMotion, okay? The storage vMotion is successful, and he's able to, and the overloads go away. Okay, the next time this should just repeat. So these are the problems we're dealing with. At the higher, this is a specific example, but there's a whole bunch of examples like this where workflows are just really tricky and hard. Storage management is just a really hard and tricky problem, and we're working hard to make that easier for you on our roadmap. The key issues here are what place should the virtual disk go, in what we call initial placement. Furthermore, at runtime, as workloads change, workloads may get hot, okay? Or there may be imbalances. How do we fix those? What about out of space? How do we avoid that type of situation without you constantly having to worry about it? Can we automate these things for you? And that's what we're going to be talking about today. Okay? So, I've already given you the outline of the rest of the talk. I'd like to invite Min Wen to come up and take us through the next part.
No? Okay. Okay. So, what's the solution we come up with for the problem that Irfan just explained to you? With storage DRS, we are going to introduce a new managed object called Datastore group. As the name suggests, it's just a group of data stores that the admin decides to put into the same group. And that's the storage equivalent of DRS clusters. Once the admin creates a group of data stores, the group becomes the load balancing domain for storage DRS. That means the admin no longer needs to worry about the detailed placement of VMs into individual data stores into the group. Storage DRS will make sure space and I/O load are balanced across the data stores. So this is the overall architecture with both DRS and the storage DRS in the picture. As we already know, DRS is a component of the vCenter server. It manages clusters of ESX hosts by communicating to the host through a bidirectional channel. The host will send performance stats about VMs to vCenter. And with the performance stats and configuration as input, DRS make decisions about placing VMs onto ESX host for CPU and memory resource balance. And once the placement decisions are made, they are sent to the ESX host for actual execution through vMotion. And at this level, storage DRS works in the same way as DRS. It's also a component in the vCenter server, and it also communicates with the host. It collects, in this case, it collects space usage and I/O stats from the host. And with that input, as well as storage configuration as input, storage DRS makes decisions about placing VMs onto data stores. And once the decisions are made, they are communicated to the ESX host again for execution through storage vMotions. Now let's talk about the relationship between the existing DRS clusters and the new concept, the new object called Datastore groups. Basically, we are supporting all the existing configuration between host clusters and the data stores. That means a single host or a single cluster can connect to multiple data store groups. And a single data store group can also be connected, can be shared by multiple hosts or multiple clusters. So the relationship is many to many. We are not putting any additional constraint on that. At this point, let's keep in mind there are some restrictions on vMotion and storage vMotion. To vMotion a VM from one host to another, the VM has to be stored on a data store or a data store group that's connected to both the source and destination host. Okay, so that's the restriction on vMotion today. And for storage vMotion, if you want to move a VM from one data store to another, both data stores need to be connected to the same host, actually the host that the VM is currently running on. So that's the restriction on the storage vMotion. And in the future, when we have vMotion anywhere, these restrictions will likely go away. Now, for storage DRS to do an optimal job of load balancing among the data stores in a group, ideally, the data stores and hosts are fully connected. That means storage DRS should be able to move any VM running on any host from any data store to any other data store. That's the ideal case. But that's not required or enforced. The admin is allowed to create a data store group with partial connectivity to some host. And in that case, storage DRS will continue to work, and it will do a best effort load balancing given the partial connectivity. Okay, so here I will briefly talk about the key capabilities of storage DRS. First, when the admin creates a data store group, storage DRS will hide all the details about individual data stores within the storage group from the admin. One of the operations the admin can do on the created data store group is to create VMs or virtual disks in a group. And instead of selecting individual data stores for the VM files, the admin just point the VM at the data store group object, and storage DRS will take care of the placement. And when it does the placement, it considers both space and I/O load and the compatibility between VMs and host and supported features and other rules that we allow the user to set, such as affinity rules that I will talk about in a minute. And once the VMs are created and powered on and put into use, they may grow in their space usage. For example, when the applications write to a thin provision disk, the disk will grow because new blocks get allocated. And different VMs or different applications will exhibit different I/O performance characteristics. So over time, even though the initial placement is load balanced, the data store may become imbalanced because of the new workload and because of the new space growth. And storage DRS will monitor the space usage and I/O performance periodically. And whenever a bottleneck is detected, it will recommend storage vMotion to fix the bottleneck. And we also offer fine-grained control on VM to data store placement, and that's similar to the affinity rules in DRS. By default, all the virtual disks of the same virtual machine are placed onto the same data store. Some admin think that's easier to manage, but the admin can also override that default rule, so give storage DRS more flexibility in placing the virtual disks. And the admin can also specify that one or two or more virtual machines are anti-affine to each other. That means they cannot be placed on the same data store. And the use case for that is, suppose you have a cluster of web server farms, and they basically have replicate disks, and they are redundant copies of each other. In case some of the data store went away, you still have the other ones. So you don't want to place them on the same data store. And another rule that we introduced in storage DRS that's not available in server DRS is intra-VM anti-affinity rule. The admin can specify two virtual disks or two or more virtual disks of the same VM to be placed onto different data stores. And the use case for that is, you say you have an Oracle database server VM, and it has a database disk and a log disk. You want to put them onto different data stores. In case one fails, you can recover data from the other. So this particular animation shows there's a VM with intra-VM affinity rule, and storage DRS will place both disks of the VM onto the same data store, and also will always move them together in case they need to be moved. We also support data store maintenance mode. That's very similar to the host maintenance mode. The admin can request a data store to enter maintenance mode so that it can upgrade the software or hardware for the data store. And storage DRS will recommend evacuation moves from this data store to the other data stores in the same group. And for the evacuation recommendations, we'll try to do load balancing among the remaining data stores, and we'll also enforce all the affinity rules that the admin has already set up. And in addition, in case the admin wants to expand the capacity of the data store group, he just needs to add new data stores to it. And when a new data store is added, it's a very easy operation. The storage DRS will start to move VMs from the existing data store to the new data store, so the load will balance within the new group. Okay, so since most of you have used DRS, I hope all these concepts are very familiar to you. But yeah, if you can you use the mic for the question? Okay, go ahead. I will repeat. Right. So in DRS, we do have admission control. And for storage DRS, For the first version, we are not thinking about supporting controls like reservation or limit, but we do admission control based on space availability. So we will not place a VM onto a data store if that data store doesn't have enough space for it. Yes?
Does that apply to thinly provisioned VMDK?
The question is, does that apply to thin provisioned VMDKs? Yes. Currently, we do a conservative assumption that the space required for a thin provisioned VMDK is the configured disk size. So we'll place, yes? The question is, do we consider this as complementary to the automated balancing that some array vendors have, like EMC fast auto-tiering? We do think it's complementary. For example, EMC fast is mostly doing automated migrations between different tiers of storage, and we are doing migration between similar storage. Okay, yes? So it's the question about how does a physical host that's connected to the same spindle or array but outside the virtual center, does that host have an impact on this? Yeah, that's a very good question, but the answer to that will be somewhat long. So let's take that in the end, toward the end of the talk. Yes? Okay, the question is, does this use the storage API to offload the migration workload to the array? The answer is depends. Storage DRS is a feature that's built on top of the storage vMotion capability, which is also part of the vSphere platform. And if the underlying storage vMotion supports the vStorage API, then we'll automatically take care of that. That's a good question. We do have a control knob to turn the I/O-based load balancing off for that particular use case, and I will talk about that when I walk through the screenshots. Okay. Yes? Yeah, I think that question was also asked in the beginning. The question is, how does this interact with the automatic or transparent migration of data inside the array? Yes, that is a very good question. And that has a lot to do with our I/O load balancing, online modeling, and algorithm. And I'll leave it to Irfan to address that in the end of the discussion. Okay. Okay, so in the next section, I will go through some UI screenshots to give you a feel how this feature might work. The first workflow I will show is how to create a Datastore group. Since a Datastore group is a child object of a data center object, you just right-click on that data center object and select the new data store group menu item. And in this screen, you just give it a name, and you can decide whether or not to turn on storage DRS on it. So just to mention, you can create a data store group without configuring storage DRS on it. In that case, the data store group will just function mostly like a data store folder, but you can also get alarms, events, and stats at the folder level. Okay. And this is to configure the automation level of a data store group, similar to the automation level of DRS cluster. So if you have used DRS, you notice the data store group doesn't have the partially automated mode. And that mode in DRS is for automatic initial placement. But for storage DRS, the initial placement or provisioning operation is already interactive. So there is no use case for automatic initial placement. And the automation mode here, manual versus automatic, only apply to the load balancing recommendations. And in this screen, you can set more control knobs on storage DRS. As mentioned earlier, you can turn on or turn off the I/O metrics for load balancing. Okay, and for space balancing or out of space avoidance, you can set a per data store threshold on the space utilization. By default, it's 80%. That means as soon as any data store exceeds 80% space utilization, storage DRS will start to recommend moves from that data store to other data store with more space. Yes?
Again, this includes the fully inflated thin provision disk.
So to exceed the threshold, we use the actual usage, not the provisioned space. Okay. And to control the I/O balancing feature, the user can set a per data store latency threshold. By default, it's 15 milliseconds. That means if all the data stores' latency is below 15 milliseconds, then no I/O balancing will happen. And if any data store exceeds 15 milliseconds, then we may or may not start recommending moves. In this screen, the user select the, yeah, go ahead.
May I come back to the threshold of the latency?
Uh-huh.
It doesn't make sense just to keep the migration off when it once happens. How long are you waiting for this to initially?
Okay. That's a good question. The question is, how long do we wait after a data store exceeds the latency threshold? The threshold is compared against a metric, the latency metric that is the 80th percentile of latency within the last 24 hours. So if a data store has to have a latency above that threshold, 80% for like 80 percentile number of the latency for any data store above that threshold within the last 24 hours, that's the criteria for kicking. Yes?
It might be worth visiting as a configurable parameter.
Is that a configurable parameter? It could be, yeah. Okay, so in this screen, you select the data stores to add to this data store group. And as mentioned earlier, you are encouraged to select the fully connected data stores, meaning the data store are connected to other hosts, but you are also allowed to select partially connected data stores. And once you complete all the steps, you will be shown a summary page about what you have just done, what's your config options on the data store group, and after you click finish, the data store group will be created. The next workflow we are going to show is how to create a virtual machine in the data store group. Oh. I went back. doesn't work anymore. I think it's... Okay, back on track. So there is already an existing workflow for creating a VM on the standalone data stores. It's our goal to minimize changes to that workflow with storage DRS. So here I will only talk about the incremental changes we added to the VM creation workflow. In the screen where the user used to select data stores for the VM, we are adding the data store group as a selection candidate alongside the standalone data stores. So the user can select the data store group, and by default, storage DRS will recommend the initial placement of the VM onto the group, or onto individual data stores in the group. But the user also has the option to disable storage DRS just on that VM and select the data store by himself. So if the user checks that box, then it will enable the individual data stores in the bottom of the screen, and the user will be able to select individual ones. And after the user completed all the existing steps for creating the VM, the summary screen is shown to the user. The only difference here, there are two differences for storage DRS. One is at the storage line. The line for storage will be showing the storage group, the data store group that the user has selected, as well as the top recommended data store from that group that storage DRS has just recommended. That's the highlighted item on the top. And if the user wants to see all the recommendations, in addition to the top recommendation, he can check the box on the bottom, and next screen will show all the recommendations. And this is the traditional way of showing DRS recommendations in the power on case. And the third workflow we are going to show is how to add a intra-VM anti-affinity rule. Again, just a reminder, this rule specifies that multiple virtual disks of the same VM should be placed on different data stores. So you specify the type of rule, you select the VM and select the disks. And you can see a summary of all the rules that you have created on this particular data store, on particular data store group. And next, you might want to go to the storage DRS panel of the data store group and look at the recommendations. So here, you just created an anti-affinity rule, and the rule is currently violated because the two disks are on the same data store. And storage DRS recommend to move one of the virtual disks to another data store to fix the rule. So it's not showing in the screenshot today, but for storage DRS, we have a new feature that you can generate an event, and you can subscribe to that event whenever storage DRS made a new recommendation. So this way, you don't have to hire someone to sit in front of the screen and monitor the recommendations all the time. And instead, the admin can receive an email notification on his iPhone, for example, or Android, and whenever new recommendations are made. That's not a commercial. Okay, so the last workflow I'm going to show is the data store maintenance mode. The admin right-click on the data store in the storage DRS group and select the menu item, enter maintenance mode. And then synchronously, we'll pop up a screen of recommendations for this data store to be evacuated. So this recommendation is all about moving this VM from this data store to another data store in the same group. Okay, in some cases, we may also do some defragmentation in the other data store group in case there's a big VM that cannot fit onto any of the existing data stores. And again, this is also an improvement over existing DRS, because for DRS, you don't get the pop-up. You have to go to another panel and look for recommendations for host enter maintenance mode. Okay, so that's all the screenshots we have today. Next, I will be talking about the space balancing part in the storage DRS algorithm. And then I'll give the stage back to Irfan to talk about I/O balancing. Yes?
Along with DRS, are there any plans that you may kind of change it under the Datastore group as well? So one failed will fire up to the
Okay, so that's a good point. Do we have HA equivalents for storage? Ooh, that's a good question. We'll be working on that. Yes? Okay. Okay, so the question is, if you request the data store to enter maintenance mode, but there are not enough space in the other data stores to evacuate, what happens? What happens is the user will be shown all the faults. Things like, we cannot evacuate this VM because there's no space on other data store. And the user will have two choices. One is to cancel the whole maintenance mode operation. Okay, then we go back to normal. And the other choice is the user can continue the maintenance mode operation, but ignore all the faults, but then the user will be responsible for evacuating that data store himself. For example, by adding a new data store or by deleting some VMs from the data store. Yes? I'm sorry? Okay, how does SRM support storage DRS or vice versa? That's a good question. And right now we are dealing with the problem of support between SRM and storage vMotion. So until that problem is solved or addressed. Okay.
Just strictly a VMFS file system, they just work on.
Does it restrict to VMFS data stores? No. You can, storage DRS can work on both VMFS data stores and an NFS data store or any other type of data store you see in a VI environment. But there is a restriction that you cannot mix different type of data stores into the same data store group. And that's what I mentioned earlier as similar data stores. Okay. So what do you mean by similar data stores? It's mostly up to the admin. If the data stores are similar enough that the admin no longer cares which individual data store to put their VMs on, they can give up the control to storage DRS for the placement, then they are similar. So examples are they have similar data protection mechanism, like they are all RAID 5 data stores. And others are they have similar security mechanism. They are behind the same firewall, things like that. Maybe same cost, to some degree, similar performance. Yes?
Are you going to make recommendations on the number of data stores and data store group, like 32 or 200 or 400?
Is the question about how many data stores do you support per group? Okay, so we are planning to use more or less the same load balancing algorithm as DRS. And that algorithm currently supports 32 hosts per cluster. So most likely, we will be supporting 32 data stores per group. Okay. So one of the first questions people will ask when we first introduce storage DRS is, how does storage DRS interact with DRS? Okay, so at a high level, storage DRS functions or places VM onto data stores at the VM creation time. And DRS places VMs onto host at VM power on time. So they happen at different time or different stage of the VM's life cycle. And For the dynamic rebalancing, storage DRS runs at much lower frequency than DRS. Basically, it may recommend a storage vMotion once every few days, but DRS may recommend vMotions a few times each hour because vMotion complete in a much shorter time. So at this level, these two features are relatively independent of each other. But the intersection point is the storage DRS placement. When storage DRS places the VM onto a particular data store, then at power on time, DRS can only power on the VM on one of the hosts that's connected to the data store that storage DRS selects. Okay, so basically, storage DRS placement will restrict the VM, the host selection for DRS. And DRS, in turn, has similar impact on storage DRS, but we are less worried about that because the DRS placement is more short-lived. Okay, it changes more frequently. It's too frequent that it will not likely have a real impact on storage DRS. So we have been focusing our efforts on the storage DRS placement, considering the DRS metrics as well as the storage metrics. Okay, so basically, to select the best data store to create a VM on, we would not only consider the I/O load, space usage of each data store, we'll also consider how many CPU resources is each data store connected to, and how much memory resource is each data store connected to. As well, in addition, what are the VM's reservations that's already running on the host that's connected to a particular data store? Basically, we count the free CPU and the memory resource that's connected to each data store. And if different resources give different preference to different data stores, like data store 1 has very good space capacity, but data store 2 has very good CPU capacity, then when different resources have contradictions about their recommendation, we use a weighted sum of the metrics across different resources. And for the resources that's more contended, it will have a higher weight in the weighted sum. So, and based on the final metric that's integrated across all the 4 resources, we will make the recommendation for data store. And that is done in storage DRS at VM creation time. And DRS placement at power on time or at runtime just continue as usual. Okay. So this is an example. I need to go a little quicker because we are running out of time. So this is an example about how the data store and the host placement works. We have 3 data stores, and they have different I/O and space capacity and connected to different hosts. And we compute a metric for each resource. The higher the metric, the more free resource for that data store. And for this particular example, let's assume CPU and memory resources are more contended. Therefore, they will have a higher weight in the integrated metric. So although in the actual algorithm, each metric is a numeric number, obviously, and it's normalized to the range of 0 to 1, but for simplicity, we're just showing the nominal values, high, medium, low. So based on the integrated metric, data store 3 has the most free combined resource. Therefore, we choose data store 3 as the destination for this initial placement. And at the power on time, DRS will choose one of the hosts that's connected to data store 3 to power on this VM. Okay? So the next topic is out-of-space avoidance or space balancing. That's part of the storage DRS load balancing algorithm. Again, the users can set the control about per data store space utilization threshold, which is 80% by default. And storage DRS will monitor the space utilization of each VM and each data store periodically. And whenever any data store exceeds the 80% threshold, storage DRS will try to move some VMs from this data store to another data store. And when storage DRS select the destination data stores, it not only look at the current space usage of the destination data store, it also considers the potential space usage growth on that data store. For example, thin provision disks may grow over time, and disks with snapshots may grow space usage over time. And we look at the history of the space usage, and we predict or estimate a growth rate per disk or per VM, and aggregate to per data store. So we will select a destination data store as long as the data store will not grow out of space in a short period of time, for example, 3 days. And we also consider the cost of the move. Basically, powered-off VMs don't have any I/O activities, so those VMs are easier to move because they have very low move overhead. But VMs with busy workload, especially a lot of writes to their virtual disks, are harder to move. They have higher overhead, so we'll prefer not to move those VMs. Okay, so again, here's an example about how the space balancing algorithm work. We have 3 data stores. They have different current utilization as well as different growth rate. And data store 3 currently is above the threshold, and we try to move things out of it. And between data store 1 and 2, we have to choose which one is a better destination. Even though data store 1 has a slightly lower utilization at the current time, it has a higher growth rate. So we predict it will grow out of space sooner than data store 2. And it's sooner enough that we choose data store 2 as the destination. Yes?
What's your growth sample window? How long are you looking at the big growth? What period of time?
We are looking at roughly 1 week worth of history to estimate the growth rate. Okay, so this is the utilization and the growth after the move. Okay, that concludes my part of the talk, and I'll give the stage back to Irfan.
Thank you.
Can you hold your question till the end of the talk? Okay, good.
Okay, so that was a lot of material. Can you guys hear me okay? So we talked about the problem. We illustrated the problem, trying to channel VC administrators. We looked at the types of abstractions we're trying to introduce to ease the storage management problem. We talked about what a data store group is. By the way, the data store group is just a working title. And in fact, I think I'm going to blog about this, and I'll have a prize for the person who can come up with the best way, the best name for this abstraction. So look out on my blog for that. And then we looked at kind of the features that we're talking about, things from maintenance mode to ease, evacuation and so forth. We talked about affinity. We talked about space load balancing. Remember at the beginning of the talk, I talked about how this project has kind of been a 3-year project as a skunkworks project inside the company. The longest pole in that was what I'm going to talk about here. Okay, so my objective in the next few slides is to be as interesting as possible to keep you guys up, but really the goal is to give you the rules of thumb and the conclusions from that 3-year study that you can even take back today and use. Okay? Now, of course, I'm going to be talking about the algorithm we're trying to automate, but these lessons are useful for you even today. So let's start out with some basic observations. Okay? Almost everything I'm going to talk about here is new, never been done before in the industry. We studied published material. We studied academic literature. We studied state-of-the-art products that people have developed, and no one was able to solve this problem, which is why it took so long. Okay, so 4 charts. Top left, at the left-hand side, actually, is data store 1. The top left is the latency plot, and the bottom left is the throughput plot. So we're going to go through an exercise of comparing these two data stores. Now, the black dots is the current operating point for these two data stores. The x-axis is load. Now, we can talk a little bit more about what that load means. I can refer you to some literature about how we define load. And it's a really interesting question. But for now, let's just call it load. Okay? Now, what load means is if you add a VM to a data store, it brings with it its load. If you add another one, you move towards the right on the x-axis. If you add another one, you keep going. So that's what's happened. So these two data stores have been loaded with a certain number of VMs, and the current operating point is that black dot. Now, imagine that this was the problem confronted by the I/O load balancing algorithm in storage DRS. Okay? Clearly, the latency and the throughput are different between the two data stores. Now, for the next little while, I'm going to focus on the latency part. So let's just talk about the top two plots. Suppose that we looked at the situation and we said, look, the latency being seen by all the VMs on data store 1 is much higher than the latency being seen by those on data store 2. This looks like an imbalance. Let's see if we can correct this imbalance. Why is it an imbalance? Because it's not the fault of the VMs that are located on data store 1 that they ended up there. We placed them there, probably automatically. Or the admin might have placed them there. It's not the user's fault. It's not the end client's fault. Okay? So if we balance things out, then everybody ends up in a similar situation. That's the kind of goal that we have for load balancing. So back to our situation. The arrows on the top, they're a little small. You might have to squint from the back. But that's the unit of the VM that we're considering moving. Obviously, if you move away from data store 1, the operating point is going to shift to the left. Now, if we look at the top plot's latency, by moving to the left, that means the dot will move down on the latency plot, right? And of course, if you move a load, a certain amount of the x-axis range over to the data store on the right, what's going to happen? The dot is going to move up the latency line. Okay? Now, before I go further, let me talk about what this latency line really is, because the fact that it's even linear is shocking, and it was shocking for us when we discovered it. And this is, this is something that hasn't really been proven using first principles by anybody, and that's the stuff that makes our work so interesting and so unique, is that we've been able to show that those curves are actually linear, which allows us to do this prediction. So let's actually go ahead and do the prediction. So we look at this situation and we say, if we took that VM and we moved that VM off of data store 1 onto data store 2, the latencies would change as follows. The black dots would move over to the new projected operating points of the blue dots. Now, notice the key thing from this slide. Notice that the average decrease in latency on the data store 1 is more than the average increase in latency on data store 2. That is the nugget that I/O load balancing and storage DRS is built on top of. Because the reason why that happened is because that slope of the data store 2 latency line, which is the top right plot, is lower. Now, why is it that different data stores can have different slopes like that, different curves? The reason is, it's actually quite intuitive. If you have a more powerful data store, if you have a more powerful storage array, as you increase load, how does it respond? It responds by degrading in performance less compared to a less powerful data store. Seems simple, right? If I have more disks, okay, you throw more workload at me, my performance is going to get worse, obviously, but by not as much as the other guy who's got half the disks. Again, this is the key thing that I/O load balancing is built on top of. Now, you can use this kind of behavior, and I'll refer to the published work on this in a second. You can refer to this type of behavior even in your own environments. As a side note, if we look at the throughput plots at the bottom, notice that throughput saturates. Okay? Again, what I'm trying to do is I'm trying to impart the lessons that we've learned. If you look at the throughput plot, you'll notice that in each case, throughput saturates. We all know this, right? At some point in time, no matter how much more load you throw at a device, you can't get any more throughput at it. It just maxed out. Of course, latency keeps going up, right? So where you want to operate ideally is a good balance between increase in latency and the extra throughput. Now, in this particular case, in this situation, the bottom right plot, you will see that the throughput increased on Datastore 2 much more than the decrease in throughput on Datastore 1. So this is the kind of ideal thing that automatically I/O load balancing in storage DRS is looking for. It's looking to figure these patterns out, and once it's got them, then it can do the analysis to say, look, how do I balance in the best optimal way possible? I'll take a question maybe. Aha! Brilliant question. I'll talk about that in a minute, okay? Hold on to that. Really good question. Now, let me be funny about it, though. Ideally, the storage array would just tell us. But they're not so nice. Where's EMC? Where's NetApp? Back there somewhere. Okay. And all the other vendors, too. They won't tell us. So we just got to figure it out on our own. And that was the fundamental challenge. Okay, so the key is, as a result of storage I/O balancing in storage DRS, we have data that shows that you can achieve average latency and drive it down. Average throughput either ends up being similar because throughput is a thing that kind of saturates at some point in time, so you can't always make it better. But in a lot of cases, we can make it better. Next couple of slides, I will show you this. Okay, so now, one of you asked about how is it that we can figure this stuff out? Seems like it works in PowerPoint, but can you actually make it work? So there's a couple of things in load balancing, okay? Number one, models, okay? Those relationships that I talked about. Number two, using those models to do something interesting. So I'm going to talk about, in my second main bullet, I mentioned two types of models, device and workload. Now, device is that latency slope with the different slopes depending upon how powerful the device is. So we need to capture that online. I'll talk about how. Okay. The second thing is workloads, and I'm going to spend a little bit less time on that. We have a paper that I can refer you to, and the reason why I'm going to spend less time on it because not because I don't think it's interesting. I think it's really cool. It's just that when I was giving the practice talk and I had the equation up, people said don't. That's a cardinal sin. Don't put up equations in VMworld talks. I mean, okay, so I took it out. Okay, I think it's really cool, but you'll have to read the paper for that. Okay, so. And here's the reference. So when you look up the slides, you can actually just go and read the paper. It's a really nice, easy read. Okay, device modeling. So here's the motivation for device modeling. We know that an arbitrary LUN, or NFS volume that gets exposed up to vSphere, has unknown properties. It could have different number of disks. It could have different disk types. You could be an SSD, I didn't even mention SSDs in that case, but you could have SSDs all the way down to SATA drives, 5,400 RPM SATA drives, okay? Unknown. Here's an example. Let's say we're given two 1 terabyte LUNs, okay? And we said, okay, load balance in between these two. We know nothing about them. It might actually be the case that they look the same, right? But it might be the case that one of them is 20 disks, 20 FC disks. Now, FC disks tend to be a little bit smaller, or a lot smaller, than the average SATA disk. So it could be that the 1 terabyte LUNs are composed of 20 FC disks or 10 SATA disks. We don't know. Now, there's probably a 4 to 6x performance difference between those two LUNs, and we just wouldn't know it. So, of course, the question is, how do we know it? Why am I standing up here so confident that we can figure this stuff out? Now, that goes back to those plots that I was talking about earlier. Here, what we did was, to demonstrate this, what we did was we took one of the vendors, and this applies to multiple vendors. I mean, we have hundreds of data points across storage arrays to, some of that in the paper and other data we can expose to you. We know that this relationship holds. What we did was we injected a very simple workload that took like 30 or 45 seconds to run. Okay? So it's just a few data points, right? 1, 2, 3, 4, 5 data points in that case. And we changed the load, in this case is outstanding IOs, and just measured latency. It takes 30 to 45 seconds to measure. Okay? And we did that for 4 different disks, 4 different LUNs with different number of disks behind them, all else being equal. The type of disk, nothing else changed, right? And you can see that the performance as predicted by our technique, which is this slope, okay, matches the number, the proportion matches the number of disks. Now, we've done this for FC versus SATA. We've done this for devices with more cache versus less cache, and so on and so on and so forth, and the relationships hold up the way you would intuitively expect them to hold up. So this is the magic sauce as far as device modeling is concerned. A lot more details there, but I'm abstracting. Yes?
Did that hold true for concatenated LUNs?
Very good question. The way we measure is a completely random read across the surface of the disk, so I believe we should be able to capture that, yes. It's a good question. Caught me off guard. I haven't heard that question before. Very good. Yeah, Meadowlands, yes. Yeah, so we should be able to. Okay, now, so I've talked about device modeling. I've tried to build this intuition that latency is the key metric because the latency is the one that just keeps going up. And it's linear. And anytime you have a linear relationship, consider yourself lucky. It's hard if it's a nonlinear relationship because now you've got to do all kinds of numerical fitting. Okay. So workload model. Here we have to be very nuanced. In our case, we actually take 4 different workload parameters. We measure these online as the workload is executing. Okay? We're not asking for users and system administrators to tell us. That's too cumbersome. We actually measure it ourselves. You run the workloads and forget about it. We'll go and actually figure this out on our own. We use that and the equation that's erased from this screen, and we actually come up with a workload metric. So now we have a device model and we have a workload metric, and now we can go and assign workloads to devices in proportion of the sum of the workloads with respect to the devices. Some of those are details that we won't have time for, but I can get into. Quick question?
So if I understand, you're considering the consistency of quality of the workload when workload loads actually vary very dynamically based upon the activity.
That's a great question. Okay. So workloads change over the course of the day, and we recognize that. And usually, it's not just the workload. Usually, you are concerned about the peak workload. And Min-Wen actually answered this earlier as well, but in a different context, which is that we were looking at, when we look at latency as a threshold, we look at the 80th percentile. And in fact, you are the one who had asked for that to be a configurable parameter. Well, the same thing is applying here. When we're talking about the device metrics, we look at 80th or 90th percentile, depending upon which metric. When we look at the workload profile, we're also looking at the high percentiles. What that means is, in the peak 2 hours of the day or the peak 1 hour of the day, what was the workload like, and build that model based on that. Okay? Because that's what people really care about. When you're idle, don't make load balancing moves based on the idle periods. That was the observation that you had made, and we had made a similar observation. Okay, so now, the proof is in the pudding. So next couple of slides, I'm going to go by pretty quick, but interesting stuff. This is the stuff that I promised it would be worth sticking around for. What we did here was we took 3 LUNs. Okay, this was on I think, fiber channel. And we placed some workloads based on the total space usage, and we balanced out the space usage. It just basically randomly placed the workload such that the space was balanced out. Okay, this is the kind of thing that people do today. I would do in the absence of the algorithm that I'm talking about. I would kind of try to balance space. Now, notice the captions at the bottom: 9-disk LUN, 6-disk LUN, 3-disk LUN. The algorithm doesn't know this. I'm just putting that up so that you would be able to compare. And we ran the algorithm against this, and on the top left, you'll see the current throughput and the latency before the algorithm ran. So we ran the algorithm. It recommended some moves, and this is the shocking part. It recommended almost everything to be moved off of the 3-disk LUN. Okay? And actually, the 3-disk LUN really sucked because it had low cache and everything. Okay? And it moved almost everything off of it, just left one workload on there. And the 6-disk LUN had a couple of workloads left on it, and the 9-disk LUN ended up with everything. Okay? And the 9-disk LUN, in this case, actually had bigger cache and a few other parameters that the algorithm was just able to figure out on its own. So, what kind of throughput improvement and what kind of latency improvement did we get out of this? 35% throughput improvement, 11% latency reduction. Amazing numbers. Okay. No, okay. Well, you guys weren't going to do it. Okay. So.
We're in awe.
Yeah. Okay. I should have waited. Okay. Okay. So. This was we have hundreds of data points like this. I just picked kind of around the middle. There are cases we can get better. There are cases where throughput doesn't improve much because throughput's already maxed out. Remember, that's the metric that doesn't, beyond a certain point, doesn't improve. But latency, most of the time, we can improve. The ultimate test, however, is to pit man versus machine. Okay? Now, if IBM can have Deep Blue versus Gary Kasparov, okay, we decided to go around VMware and try to find Garys, basically the equivalents of Gary Kasparov, to pitch against our algorithm. I mean, we thought this was fun. Of course, we never thought we'd win, okay? But turns out we did not too bad. Okay, so 13 VMs. Now notice the workloads. This is serious stuff. 3 DVD store workloads running on real Oracle. I think that one is SQL Server. 2 Swing Bench workloads running against Oracle. 4 mail servers, 2 OLTP, 2 web servers. This is real hardcore stuff. Okay. And the hardware configuration is not too important to worry about. We just had 3 LUNs. So here's what happened. We put man versus machine, and the leftmost plot is the initial conditions. This is the space balance configuration that we always try to compare ourselves against, because you need some baseline to compare against. So what we do is just randomly pick workloads so that they're kind of space balanced out. Then we ran storage DRS. Now, with respect to these experts, I told you that they were people from within VMware. We actually went and found 2 world-class storage performance experts. Okay? Happen to be working at VMware. Haha, names will be elided. For the protection of said engineers. Okay. Now, so what happens? Check this out. This is throughput on the y-axis. Now, expert number 1, okay, so the shades of blue are the amount of throughput coming out of each data store. So those are the 3 shades of blue are data stores. Expert 1 beat us on throughput by a little bit. We were a little disappointed. It's like, we thought we're pretty close. Okay, maybe almost within error margin. Not bad. Okay. Expert 2 showed up with, his configuration, and we beat him. We were like really happy. But we thought, okay, we didn't beat him by much. Until we looked, okay, so we figured, okay, this is throughput, right? So maybe the device was already saturated, no big deal. So we looked at throughput. So next is latency. Here's the kicker. Now, focus on the green bar, because that's the aggregated IOPS-weighted latency that the workloads see. Space balance was terrible because that blue data store, which was the least powerful data store, all the VMs there were getting very high latency. So rather than just try to compare across all bars, we just plotted the green bar alongside it, and that's, like I said, the average latency the VMs would see. Now, expert 1, we embarrassed, okay? Now, he managed to beat us by a little bit on throughput, but we really creamed him on latency. Now, the question, and the expert 2, we also beat. So storage DRS was able to do really, really well in this configuration. Okay. Now, you may ask, what's wrong with the storage performance engineers working at VMware, okay? But don't ask me that, because I'm going to come after you and say, what's your configuration, okay, and put you on the spot. These guys are actually world-class, okay? This is we're talking about very, very serious experts here. But the thing is that Deep Blue was able to beat Kasparov, not because Kasparov is not smart, okay, but because there's so many dimensions to the problem. There are just so many numbers to crunch. We printed off so many pages for these guys. We allowed them to have any data that they wanted, these 2 experts. So they knew everything about the storage arrays, down to the cache sizes, down to the block sizes. They knew everything about the workloads, even stuff that the algorithm wasn't told about. Okay? Now, with this many pages of data, they sat down and spent a few hours. They came up with some pretty good results, right? Better than the default. But the question is, why bother? If you have an algorithm that can actually put that much data and resolve it and come up with an answer, that's the ultimate goal here. So it's not that humans can't do this job. Okay? I think if these guys tried again, having seen these results, they might actually beat us. The question is not that. The question is, why bother? Okay? And that's what we're aiming to do, to bring an automation level to our customers where you simply do not have to worry about this sort of thing. Okay, so we're right at the end, but this is my experience is every time I put up the conclusion slide, people start to shuffle. It's like, oh, it's all over. It's not all over. Hang in there just a second. Because we really need your feedback. So it doesn't have to be right now, but please do fill out those forms. I was here a year ago, talking about storage eye control, the check preview, and the feedback you guys gave us went into prioritization for that feature. Okay, and the reason why we were able to deliver that in a year is because of the prioritization we were able to do based on your feedback. So I'm not going to recap the talk. You guys, it wasn't that long, but here's what we need. We need to get help in prioritizing stuff that we haven't even talked about today. It's stuff that we're trying to figure out how to do. Well, what do we put in front of the rest of it? Space quotas and reservations is one thing I really need you to think a little bit about in your environment. How do you want this stuff implemented? What should happen when somebody runs out of quotas? Should we just turn off the virtual machine, just alarm? Like, what are the semantics that you want out of this stuff, right? What do reservations mean in terms of space? And how strict should we be about them? And so on and so on and so forth. So there's a lot of features that a lot of aspects of this product that we need help on to prioritize. So please take the time to actually tell us about this in your feedback. Here are the takeaway points. Okay. Our goal in the resource management team is to say goodbye to over-provisioning. We've done this in the past. We've done it with storage I/O control, which we really believe that once you get experience with, you're going to be able to drive up your utilization and drive up your shared storage consolidation, because you'll have the peace of mind that during contention periods that you're going to have something, an automated feature that's watching your back. So the one thing you can do to optimize your environments today is to try out storage I control. Okay? The other thing you can do is to look forward to storage DRS, but help us, give us feedback, whether that's on forums, that's through your representatives, your VMware representatives, or otherwise. Please do take the time to do that. So I'd like to take questions at this point in time. If people need to leave, they're going to catch flights, that's fine. But I really would appreciate if we could just use the microphones. It would allow everybody, while the shuffling is going on, to be able to clearly hear the questions. Thank you very much.